Okay, let's talk about this exam. Am I recording? Okay, did everybody pick up their exam back there, that table? Okay, so I told you all when the exam started that I felt like the exam was like a 4 out of 10. That's what I said, like a 4 out of 10. I think that the grades reflect that pretty much. We had 8 A's, 6 B's, 2 C's, 3 D's, 4 F's. The class average was a 79, so almost an 80 on the test average. We had a somewhat high standard deviation, meaning that there was a pretty big spread between the grades. But you can kind of see that from this chart. It looks like an upside down bell curve almost. And what you like to normally see is your standard bell curve where you have a few over here, a bunch in the middle, a few over here. That's called standard normal distribution. But I have no problem having a bunch over here. But when you have this situation, this is a little challenging because you have a group that's kind of, we're ready to move on. And then we have a group over here that I'm concerned about, all right? And there's not much in between. Does that make sense? So, it's just the first test. So if you didn't do well, there's plenty of time to recover your grade. If you did real well, at the same time, there's plenty of time to undo that, So you don't want to take your foot off the gas. You want to just continue doing what you're doing. So, part of this, part of being a college student, part of being in a STEM field is that, you have to learn how to study. And so for the students that are over in this region, there's this famous quote by Albert Einstein. It goes, wait, is it Einstein? Yeah, his definition of insanity, have you all ever heard that before? Albert Einstein's definition of insanity is doing the same thing over and over and expecting a different result each time. So my point being, if you're over here, you need to change something, all right? You can't expect to go about studying and preparing for the exam the way you've been doing it, even if you've been doing it your whole mathematical life. Something has to change for this class if you want to see this change. So I invite everyone in the class to come sit down in my office during my office hours. You want to talk about the exam, you want to talk about your grades, whatever. My door is open to you. I can't force you to come, but I would strongly encourage anyone over here to take 10 minutes out of your life and come sit down and we can talk about, strategies for improving in the course, all right? I'd rather you do that now than at the final week of the semester come up to me and be like, what extra credit can I do, okay? I like to talk to people early in the semester when we can fix the problem, not at the end when you're expecting some sort of grade inflation, right? Okay. Any questions over, not specifically on the test. If you want me to answer questions on the test, how I graded something on your test, we can talk after class or in my office. Any like general comments or concerns about the grades or the tests? Did you feel it was fair? It was fair. I don't even have to ask that. It was a fair test. I mean, most of those problems were pretty much either directly from the homework or directly from problems we did in class. So, yeah, right. Would you agree? Yes.
What do you have decimal points?
Here?
Yeah.
That's just the way I did it. Yeah. I mean, decimal points are actually, it's kind of a big deal when it comes to grades because, you may need that decimal point to get you up to that next letter grade. And so I always round to the 10th. And so I look at the number in the 100th position and determine your number for the 10th. And I use your standard rounding, right? Does that answer your question?
Yeah, I was just wondering because most people just do whole numbers. So
yeah, we can. This is the precision I go out to the nearest 10th. Even though at the end of the day I have to give you a letter grade. Where that letter, if you end with an 89.4, right? 89.4. Technically that's a B, right? And an 89.5 should go up to a C, go up to a C. Should go up to an A, right? Yeah, I mean, I think we can all, yes? And that's what I would do if you had an 89.5. If you had an 89.4, then we'd probably have to sit down and talk. All right, let's move on, okay? There's nothing else? My daughter is in 4th grade, and she's in a private school, and every year since pre-K, she's made this thing called Pastor's List, which is a 95 average and higher on their academics, right? So last year, we pulled her out of school for a family trip, and so she missed 3 days of school to go to Disney World because my father was going to have surgery, so we had to do it before his surgery, so we had to pull the kids out of school. So the 3 days she missed, they docked her. All the homework she had, she got zeros on everything she missed. So her grade point average at the end of that quarter was a 94.81. And they did not give her pastor's list. What? Yeah. So I had to sit down with the teacher and I argued my point because in the grading scale it says this. I don't know why I'm telling you all this. Okay, so A it says 90 to 100 or something like that, and then B it says 80 to 90, right? And then C whatever. I can't think right now. 70 to 79. Hold on, I messed something up here. 80 to 89. Sorry. That's what it said, right? So what happens? Oh, I forgot the pastor's list. Sorry, this is like A is like 90 to 94, and then pastor's list, whatever, was 95 to 100. So where does 94.81 belong? Well, if you round it up, right? Yeah, but who says you round up? Right? So to me, the way I look at this is that if this is your grading scale, right, then you are not looking at decimals. You're going to the whole integers, right? You have to pick an integer for your grade. You don't get to choose 0.81. You have to make that a 94 or 95, one or the other, right? And so they made it a 94 because she did not achieve 95. So, I mean, now, I was giving the argument, you round, right? You round. And in fact, I showed the teacher the section in the book that she taught my daughter how to round. So, I told my daughter, just leave it alone. It's not worth it. And she told me, I said, some fights some battles aren't worth fighting. And she said, this one is. And so I went to battle for her, but we lost. And she needs to learn that lesson anyway. You don't always get what you want. So I still think it's wrong, but I will not do that to you. I will round, I will round the way you would expect me to round. Okay, all right. So moving ahead, are there any tests that were left up there? Al, there weren't any tests left up there? So everyone got it? Okay. All right, so if we kind of take a look back just briefly at what we've done, we started with the limit in this class, right? Well, we did some review stuff in the beginning, but we did the limit, and then from the limit was born the definition of the derivative, right? And we did derivatives with limits, and on the test there was only 2 questions where you had to find derivatives with limits. I never asked you on the test, so keep this in mind for the next test. I never gave you a function like this and asked you to find this using the limit definition. Now, if you did the bonus, then you would have had to have done that. But I didn't give this on the test, right? Like directly. The last 2 problems, I asked you for the derivative of a function at points, right? So you actually didn't have to use this formula. You didn't have to use that formula where we leave x as x, right? In the test you could have replaced, I think it was with a 1. And then you could have got around that. So on your next test, there will be a few problems in the beginning that will ask you to find the derivative of a function using the limit definition, and you have to do it this way. Even though you're going to have a shorter way of doing it, which are the shortcuts, which is what we've already started. So just keep that in mind. It's not that I forgot, it's that I just didn't put it on this test. All right? Okay, so we've talked about this. You had homework on that already. And now what we moved in from that is, okay, can we find derivatives faster? Is there a way that we can take derivatives without having to use the limit definition over and over and over, right? So we started to get these like shortcut formulas. And so what I want to do now is go through them. And what I'm going to do is I'm going to give you a list of the formulas. And we're going to do examples with each one. And then if I have time at the end, I'll prove certain formulas. Like some of them are hard to prove. Some of them are easy to prove. So let's just start out with the simplest one, right? So what we're doing right now is we are finding our formulas for differentiation. And we are in, I think, 2.3 in the book right now. Yeah, it's 2.3. And we've already done a few. Okay. So here's some notation I'm going to use. d dx. That means we're going to take the derivative and we're going to be treating x like a variable. So I want to know what the derivative of a constant is. Now we've done this, all right? We've done this. What did we say the derivative of a constant will always be? 0. Okay, always 0. So let me show you some slightly different notation. Okay, so if I write d dx of a constant c, that's the same as writing c with a little prime mark. That means take the derivative of a constant, and we know that that's 0. Now, geometrically, we can go back and do this again, because I think we did. If you draw a constant function, right, it's flat. That's the function f of x equals a constant, right? It's just flat horizontal line. And so the derivative would represent the slope of that the tangent line at some point. And because it's flat, if you go to any point, the tangent line's got to be flat too, right? So the derivative of any constant function is always 0. All right, the next thing we looked at was the derivative of the identity function x. Another way of writing that would be x prime. So what is the derivative of x? 1. Okay, and that comes from the idea that if you graph that function, f of x equals x, it's that perfect diagonal, right? That's what this function is. And so the slope of this line is 1, right? So if I go to any point on that function, ask you for the slope of the tangent line, it's going to be equivalent to the slope of the line itself. So it should be 1. All right? Then after that, we said, okay, that was x raised to the first power, but what about if we have x to higher powers? And we went through this whole development, and we used Pascal's triangle, and at the end of it all, we had a very nice formula for taking the derivative of x raised to any power. And what is it? N x raised to the n minus 1. We call that the power rule, right? And these are important. Now, don't take this the wrong way. Oops, I forgot to put 1 here. I'm not going to downplay these. These are just as important as this one, but that one will stay with you for a long time through your mathematical life, all right? So we use that. I actually proved it to you, and so I think we can put this one away. We'll do some examples with it, but and then what else did we talk about? I think we talked about the derivative of sine, right? So we said the derivative of the sine function turned out to be what? Cosine of x. So let me write the other notation. If I write sine x and I write a little prime mark, okay, derivative of sine of x turns out to be cosine x. I proved that one to you also using the limit, and we used some identities from pre-cal. And then we also visually talked about the derivative of cosine. and we said the derivative of cosine, we wished it was sine x, but it's not sine x. It's almost sine x, right? It's negative sine x. So this one I didn't prove, but I visually tried to convince you that that was true. And did we talk about adding and subtracting? I don't know if we did that, but I'll go over it anyway, okay? If this is new, then fine, I think you can handle it. So right now, this is like all we have. You give me a constant, take derivative, you got 0. Give me x by itself, take derivative, you got 1. Give me x to any power, take derivative, you got this. Derivative sine, you got it. Derivative cosine, you got it, right? So what about if we're asked to find the derivative of two functions, let's call it some function f plus or minus some function g. So this is different, okay? These were specific functions, right? This is the constant function, this is the identity function, this is a power function, this is the sine function, that's the cosine function. But this is saying in general, if you have two functions that are being added or subtracted together, how do you take the derivative?
Take the derivative
Of each one separately, and then add or subtract. So does it seem like that would be plausible? Let me see. Let me write it this way. We want add or subtract two functions. We want to take the derivative. Does it make sense that it should be the derivative of the f1 plus or minus the derivative of the g1? That you can just take the derivative of each one. Does that seem plausible to you? And that's what it turns out to be. All right? I will prove that to you at the end of class if I have time. Okay, but right now you're going to take this on faith, all right? That if you have two functions separated by addition or subtraction, that you are free to just take the derivative of each one separately. So let's do a specific example of this because we haven't really gotten into that one. An example of that would be, let's say we have the function, let's say we want to take the derivative of x squared plus sine x, right? If I ask you to find derivative of that, you have two functions, right, that are separated by addition. So because of this property of derivatives, you should be able to take derivative of each one separately. So this should be equal to whatever derivative of x squared is, plus whatever derivative of sine is, sine of x. And we know the derivative of x squared, right? That's just 2x. And we're just using this rule here, the power rule. 2 comes down, subtract 1 from the power. And then this one, we know derivative of sine is cosine, so we say plus cosine x. And there it is, right? So that's that rule in action. The way we say this verbally is that the derivative of a sum is the sum of the derivatives. Let me say it again. The derivative of a sum is the sum of the derivatives. Or you could say the derivative of a difference is the difference of the derivatives. Okay, you ready for the next rule? Yeah. Yes? No? Yes? Okay. So the next rule, and this one always kind of confuses people in the beginning when they first see it. The derivative of a constant times a function. So this is kind of like the one before. I'm not telling you specifically, in this formula, we don't know what the functions are. They're just two functions. So this rule is saying, hey, if you ever have a constant times a function and you want to take the derivative, another way you could write it is like this, right? Then what does that turn out to be? Well, we were told earlier the derivative of a constant, right, is 0, but it's not 0 if it's attached to a function. Okay? So what happens in this case, and only in this case, when the constant is attached to a function, is that what you get here is the constant times the derivative of the function. So let me give you a specific example of this. Let's say we're asked to take the derivative of 5 cosine x. All right? Do we have a constant times a function? Yes, we have a constant times a function. If I asked you to take derivative of just 5, you would say 0, right? But that's not what's happening. 5 is attached to a function. So because it's attached to the function, the answer should just be the constant times the derivative of this function. So it's the constant, I like to say, comes for the ride. Okay, it's just going to come for the ride, and nothing's going to change. It's just going to come along. So our answer is going to be 5 times, now what's the derivative of cosine x? Negative sine x. So we have to be a little careful here because that's a negative sine x. And this is not 5 minus sine x, right? This is 5 times negative sine x, which really makes that 5 a negative 5 because we're multiplying. It's multiplication, not subtraction, right? So there's your answer. Does that make sense? I mean, again, I'm just asking you to take this on faith. I'm going to try and prove it to you later if I have time. But for now, you just need to understand that if the constant's attached to a function, it comes for the ride. All right. Good? All right, so now let's get to where things start to get weird. Because I think everything up to this point pretty much behaves the way you would hope it would behave. But what I'm about to show you here is what makes Calculus 1 difficult and what makes Cal 2 really difficult. Is what happens if we have two functions being multiplied and we want to take their derivative. Let me write it the other notation because I want to stay consistent. So if we want to know derivative of a product, right? If I give you two functions and I ask you to multiply them, take the derivative, then what's the answer, right? So what do you think would be like the best case scenario that this would be equal to what?
It was the derivative.
The derivative of f times derivative of g. Wouldn't that be great? I mean, don't write that down. Because that's not what it is. But that's what would be nice, right? Because then everything would just kind of flow the way, if you add two functions, you just take derivatives each one and add them. It'd be nice if when we're trying to look at a product, that when we take the derivative, we just take the product of each one, derivative of each one and just multiply them. But that is not it. That is not it at all, in fact. It looks very different. So what it is this. What you're going to do is you're going to look at your two functions, right? You got multiplied. You're going to take the derivative of the first one, okay? But then you're going to multiply it by the second function, g, without taking the derivative of g. And then what you'll do is you will add to that the derivative of g times f. And this is known as the product rule. Very important rule. Okay? Now, I will prove this to you today. I will. When I start proving them, this is the first one I'm going to do because this one is so important. You should see the proof for it. Wow. Okay, so that's not at all what anyone would have expected it to be, right? So it's almost like when you take the derivative of a product, you have to take the derivative. It's like it takes turns. Like first the derivative is applied to this one and not this one. And then you add to that the derivative applied to this one, but then not that one, right? That's what the formula is. With me? Okay. Now, in your book, I don't even remember how it's written in here. But if you look in your book, or if you go to the tutoring lab, most of the time, the tutors are going to give you the rule, the product rule, the way it's written in textbooks. And most textbooks write it this way. Let me see. They write it f times g prime plus g times f prime. Okay, so is that the same answer?
Yes.
Yeah, because it's just like this one is really that one, but flipped. But you can flip multiplication, right? So that's the same. Then we're adding that one right there, but flipped. So these are the same exact things. They write it in a different way, don't they? And I absolutely hate this, all right? I hate this. I'll explain why. But give me an opportunity to show you an example first, and then I'll explain why I hate that formula. If I were you and you've never seen this before, I would try and memorize it this way. And yes, you need to memorize it, all right? It's not one of those things that you want to be looking at a formula sheet each time. All right, so let's do an example. An example of this let's say that we have x to the fourth times, let's go with just sine x. We're very limited on what we can take the derivative of right now. All right, so do we all agree that we have two functions being multiplied? Okay, so you have to identify that. You have to be able to see the product is between these two, right? You have a product between two functions. So this is like acting like the f, and this is like the g. And so now what we'll do is we'll just apply the formula. So according to the formula, this should be, and I'm going to take my time here, it's going to be derivative of the f1, right? So the way I'm going to write that is here's f, right? X to the fourth. I'm going to take its derivative and then multiply that times g. What's g for us? Sine x. I'm not going to touch that one, right? I'm just going to leave it alone. And then plus, I need the derivative of g, so I take my g function, put a little prime mark on it to let everyone know I'm going to take the derivative, and then times my f function is x to the fourth. So I actually haven't done any derivatives yet, right? All I've done is just kind of rewritten this using the product rule, putting the derivative on the first function, leaving the second one alone, plus derivative on the second function, leaving the first one alone. And now I just actually calculate the derivatives. So what is the derivative of x to the fourth? 4x cubed, right? So 4 comes down, subtract 1 from the power, and then times sine x, right? Plus derivative of sine x, cosine x, times x to the fourth. You're not touching that, right? And that right there is the derivative. That's the derivative. Okay? Now, we can leave it like that and we'd be correct, but I just would warn you that these two cannot go together. Right? That x is trapped in the cosine, so you can't put that together as x to the fifth. So to avoid any confusion, I would go one more line and I'd write this. I would just bring that x to the fourth out in front of the cosine, and that way I'm not confusing anyone with my answer. Yes?
The notation that you're using right now is saying we're creating derivatives and then you don't have to like put d or d of x or any of that?
Nope. This prime mark is basically me saying d dx. It's just prime's a lot easier to write. Later on, we will go back to using more of this. So do not forget it. I mean, this means take derivative treating x like your variable, right? Later on, we might be taking derivative treating y like the variable, or we might be taking derivative treating t like a variable, or v, or so we will need that notation later, but for right now, the prime means take the derivative treating x like your variable. Okay, any questions on that? Now let's just pause right now and understand the magnitude of what this formula gives us, all right? So I'm going to bring up my graphing utility. And if somebody has a calculator, this might help. Well, you know what? Okay, well, maybe we can do this. Maybe we can do it this way. You see this function right here? Right? You see that function right there? If I asked us to graph this, f of x equals x to the fourth sine x, right? There we go. Let's say I asked you to graph that. Right? You would get it on a computer to graph it, wouldn't you? All right. Can you tell me what the slope of the tangent line is at 0? So if you draw this and you go to the point, what's the point? When you plug 0 into this, what do you get? When you plug 0 in, you get 0, don't you? So we know that that point lives on that graph. Whatever this graph is doing, right? Whatever it's doing, it goes through that point. Yes? Can you tell me the slope of the tangent line there? Why 0? Why is it 0? How do you find the slope of the tangent line? How do you find the slope of the tangent line for this function? You take its derivative, right? And you look at that. So isn't this the derivative? And what would happen if you plug 0 into this? You get 0 here, sine of 0 is 0, so that's 0, and then you get 0 here, cosine of 0 is 1. So you get 0, don't you? So if I go into my calculator or my computer right now and I graph this, and we look at that point right there, we should see a flat tangent line there, shouldn't we? Okay. What about, how about at, yeah, let's do it. You're Cal 1 students, you can handle this. So what if I went and I wanted to know the slope of the tangent line at x equals pi over 2? All right? So what that means is, let's plug pi over 2 into this first. All right? What happens if I plug pi over 2 into sine? What's sine of pi over 2? 1, right? So if I plug pi over 2 into the original function, sorry, that's so sloppy, then I get pi over 2 to the 4th, right, times 1? And pi over 2 to the 4th, we could get on our calculator, it's something, right? So that means if I graph this, and I go out to pi over 2, we're going to go up to some number, and I'm asking you right there at that point, what's the slope of the tangent line? So how do you find that? You go here and you plug pi over 2 here, right? So the derivative of that function at pi over 2 should be 4 times pi over 2 cubed. That's not pi over 2, it's pi over 3. Pi over 2 cubed times sine of pi over 2 plus pi over 2 to the 4th times cosine of pi over 2. Y'all with me or not? Okay, so this piece over here is going to go away, isn't it? Because cosine of pi over 2 is 0, and that kills off this. So this is gone. And sine of pi over 2 we know is 1, right? And so what we have is 4 times this. So whatever that is, whatever that number is, that's the slope of our tangent line. So is that a positive or a negative number? It's a positive, and it's actually pretty big, no? I mean, pi is about what, 3? 3 over 2 is bigger than 1. So if you cube it, that's still bigger than 1. You multiply it by 4. So you got a slope of at least 4 on that tangent line. Yes? So I'm going to go bring up the graph. What we should see is that at 0, 0, we should see a flat tangent line. We go out to pi over 2 and go to the function. We should see a pretty steep tangent line, right? Okay, it was x to the 4th. Whoa, caps lock. X to the 4th times sine x. All right, and check that out. At 0, 0, right? At 0, 0, do we have a flat tangent line? Is our tangent line horizontal here? Absolutely, right? Okay. And then at pi over 2, so let me see if we can't find pi over 2. Does somebody mind on their calculator figuring out what 4 times pi over 2 cubed was as a decimal? Because that'll give us the slope of the line. I'm sorry? You got it? What is it? 15.5. Okay, so here it is. Here's the graph of the function, right? This function is being graphed over here. And what I can see here is that if I go to pi over 2, I have some point here on the graph, right? Somewhere. And I'm saying the slope of that tangent line is 15 point something. Does that match what it looks like is happening? I mean, this is a very steep tangent line, isn't it? It's very steep, right? Okay, so we can talk about tangent lines anywhere on this function now because we have its derivative. And that derivative didn't require too much work, right? Just the product rule? Okay. So we have the ability now to handle a lot of functions now because of that product rule. We can pretty much anything with a product we can deal with. Now, I still don't think that I have made you appreciate how good it is, so I want to look at one more thing with this function. Okay? What if I asked you to find the derivative of this using the limit definition? you're not allowed to use the product rule. No shortcuts. You would have to say, okay, the derivative of this function is the limit as h goes to 0. Well, let me write the definition. F of x plus h minus f of x all over h, right? That's what you would do. But that would be limit h goes to 0. And then look at this. What's f of x plus h? X plus h to the 4th sine of x plus h. Isn't that f of x plus h? Replacing all your x's with x plus h's. Okay, then subtract from that just the function itself, f of x. And then all of that over h. And then you go try and do something algebra-wise to make that nice. And it's just not happening, okay? It's just not happening. You're going to suffer if you try and do that. So the beauty of these shortcuts is that it's allowing us to still do this without actually having to do it with the limit, all right? So you should be happy about that. Okay, what do you think comes after the product rule? What do you think the next thing we want to be able to take derivatives of? Division, right? So we call that the quotient rule. So what if you're trying to take derivative of two functions that are being divided? Okay, so I want to take some function f and divide it by some function g, and I want the derivative. All right, what would we love it to be? Derivative of f divided by derivative of g. That would be wonderful. That's not what it is. It's this. Derivative of f times g. That look familiar? Almost looks like the product rule. Yes? But instead of plus, you put minus. Okay? And then you do derivative of g times f. That's exactly the product rule, isn't it? With a minus instead of a plus. But there's one big additional thing you have to do. You have to take that entire result and divide it by g squared. And that's your quotient rule. Very important rule. Now let me show you the way it's written in the book. Here's the way it's written in the book. G times f prime minus f times g prime over g squared. And I hate that one too. And let's see, maybe you can see why I hate them. Let me put the product rule here. The product rule that I gave you was this. Right? Plus, sorry. And the book said, what was it? I forgot. Fg prime plus gf prime here? Okay. So that's the way the book gives the product rule, and that's the way the book gives the quotient rule. Can anyone tell me why I hate that? Hate's a strong word, but can you tell me why I really dislike it? Because what? I can't hear you. It flips them. Yeah, but I mean, I'm okay with it flipping, I guess. Let me just ask you, do these look like very different formulas to you? I mean, does it look like you have to reserve part of your brain to remember this, and then reserve a different part of your brain to remember this? Where with the way I look at it, it's not like I'm, came up with this great thing. It's just like when I was looking at this as a student, I was like, wait a minute. Why can't we just look at it this way? Because to me, all you have to do is remember this formula. That's it. Just remember this one. And then when you go quotient rule, you replace that with a minus, and you divide by g squared. On their formula, you can't do that. Because if you replace that with a minus, you also have to change, you have to reverse them. And it just bothers me. Okay? So you do what you want. You memorize it how you want to. But like I said, if it's your first time, I encourage you to do it this way. I think it's just less to put in the brain. All right, you ready to see the quotient rule in action? All right, so let's do this example. Let's take, so some of my notation is going to change right now. I would like for us to look at this function. I'm going to call it h of x. And what it is a good old rational function back from college algebra. Is that not a function that you would have seen in college algebra? You've been asked to graph that? Okay, so now you're in calculus and you're being asked to find slopes of tangent lines on that function. So you need the derivative. So if I want to take the derivative of this, then I have to realize that I have a quotient, right? Two functions being divided. So my top function here, this is like my f, right? And this one right here is like my g. So all I'm going to do now is apply the rule. So the derivative should be, let's get our trusty sticks out here. Salo? Are you following so far? Yes? Okay, so we want to take the derivative of this quotient. I want us to use this rule, okay? So I've helped identify what f and what g are, right? So according to the formula, this derivative should be equal to, what's this piece for us? I'm sorry?
X plus 1.
Okay, and we want to take its derivative, right? So I'm going to write that down. X plus 1, but we want to take its derivative. And then times what? Keep going. X squared minus 4, and we need that in parentheses, right, everyone? Because it's got two terms. And then minus now the derivative of g, which is x squared minus 4, but this time we need to take its derivative, right? And then times f, which is x plus 1 in parentheses because it's two terms, and then the whole thing divided by x squared minus 4, that quantity squared. There it is. So that's just me plugging everything into the formula. Now the question becomes, can you actually take the derivatives of both those? If you can do that, we're going to be done. Well, not done, but we'll be done with the derivative part. Okay, so let's move on to the next person here. Marissa.
Yes.
So you get these very difficult derivatives. What's the derivative of this here? 1. So because there's a plus, you're doing them separately, right? So we have two terms separate. So this is like, you use the rule that if you have two things separated by addition, you can take derivative of each one separately, right? So you took derivative of x, you know that that's 1. Then you said plus derivative of 1, which you said was 0 because that 1 is a constant, right? Everyone good with that? So this top left piece becomes a 1. 1 times then x squared minus 4, nothing changes there. And then minus, go ahead, Marissa.
2x.
Just 2x. Derivative of x squared is 2x minus derivative of 4, derivative of 4 is 0. So you just get 2x from here. And then we still need x plus 1 in parentheses. And then all of it divided by x squared minus 4 squared. So this, at this point, calculus is done, right? The calculus part of this problem is done. The rest of this is now going to be algebra. Can we clean this up? So distributing a 1 through here changes nothing. Distributing a negative 2x through here is going to change some things. So I will have x squared minus 4 minus 2x squared minus 2x all over x squared minus 4 squared. Do you all agree? Can we collect any like terms here? The x squareds we can combine. So we should be getting to a final answer here pretty soon. Our derivative is, let's go ahead and put it in descending order. So what's my first term? Negative x squared. And then x term? Minus 2x. And then minus 4. All of that over x squared minus 4, that quantity squared. And you might be asking yourself, like, do I need to expand? Do I need to square that? You don't need to, okay? You can just leave it like that. And this right here, well, it's good enough. Just leave it like that. So that means if we go graph this function, whatever it does, if we want to go to a specific point, let's say we go to like, what if we go to like x is 0? Can I plug 0 in here? Yeah, you get 1 on top, you get negative 4 on the bottom, so we'd have some point on the graph, right? And if we do that, the slope of the tangent line there, we can get from this, right? Just plug 0 into this, and that'll tell us the slope of the tangent line. What do y'all think about that product rule? Okay? Question? What? Did I say product rule? Yeah, quotient rule is what I meant to say. All right, so now what I'm going to do is I'm going to put some we're going to do some problems. Now we get to really start mixing things up. Sienna? Wait a minute. Sienna, where is, what did I do here? All right, Sienna. Which rule are we going to use to take the derivative of this? Product rule. So it's obvious to you where the product is occurring, right? Right in between here, right? So according to the product rule, we would call this thing F and this thing G, yes? But see, I've already used F, haven't I? Like F is the name of the whole thing. So it's kind of weird to call this F and this G, even though like we could, but that's F. Do you see how the lettering can be a little weird? So do you want me to call that F and G and do our stuff, or do you want me to just call it something else? What would you do? You just want to keep it as F and G? Okay, so this is just so we can use the formula kind of as a template, right? Okay, so according to the formula, if we're going to take this derivative without using the limit, it should be what? I'm just going to let you lead the way here. The derivative. So you're first going to take derivative of the cube root of x. Take that derivative, and then times sine x. Derivative of sine x. There it is. That's it. That's just the setup, right? And now you have to go and ask yourself, can you take these derivatives? So Sienna, when you look at these, that one's good, yes? This one? You look at derivative sign, you're just automatic now, right? You know it's cosine. All right, so we're happy with this. This one, maybe not so much. Maybe that's going to require a little bit more thought. How are we going to do that one? I'll open up to everyone here. How do we take derivative of the cube root of x? Yeah, first do some work here on the side. Cube root of x, we want to take the derivative of it, right? Well, that's the same as x to the 1/3. And once you get it to that, we can use the power rule. So the 1/3 will come out. And then x to what power? Negative 2/3. Right? Because you have to subtract 1 from 1/3. 1/3 minus 1 is negative 2/3. And then We could leave it like that, I guess. I mean, there's nothing wrong with leaving it like that, but if we want to write it without a negative exponent, we would have to write it like this. 1 over 3, and then what root is that? That's the cube root, and inside is x squared. And the fact that it's on the bottom now took care of the negative power, right? So I moved it to the bottom, x to the 2/3, and then rewrote it using a radical. So that's that front piece, right? Yes. Okay, so now we're ready. This is going to be this 1 over 3 cube roots of x squared, and then sine x plus derivative of sine x, which we never actually wrote it down, so cosine x, and then times the cube root of x. And that's it. I mean, you could put the sine x up here on top with the 1 if you wanted to, but otherwise we have the derivative. I mean, that's it. Questions on that?
On the test, would you want us to reduce it to where you have
You mean, like, would I be okay if you left it like that?
Right.
Oh, yeah, I'd be okay with that. Yeah. That's it right now. Yeah, that's it. That's the derivative, right? All right, we're going to go off topic, but on topic, okay? I want you to think about something in college algebra, all right? Do you recall ever seeing this in college algebra? Okay, that in college algebra is a quadratic function, obviously, right? Okay, do you remember that when you were told to graph this, that the A would tell you up or down, right? And then you could go find that vertex, right? And there was a formula for the vertex. Remember the formula for the vertex? So like this one, I mean, we don't know if it opens up or down because we don't know what A is, but let's say it opens up and we have that point right there. In college algebra, we called that point HK. It's a very important thing called the vertex. And then you were given a formula that said H is negative B over 2A. And once you find out what that is, then you can get K by just plugging that answer into the function. And it was a way to find that lowest point on that graph, right? But they never really explain to you where this comes from, do they? Well, maybe some people do, but right, you just were given the formula and you said thank you and you used it, right? Okay. So I have a question for you. What is the derivative of any quadratic function? So let's take a look at this here. And remember, A, B, and C are numbers, right? They're usually given to us. So if I ask you right now, what's the derivative of A times x squared? This is a constant times x squared. So the derivative of that, the constant will stay, it'll come for the ride, and then we take derivative of that. So what would we get? We get A times 2x. I'm just going to write it like that. The A would come for the ride times the 2x. And then plus, now I'm doing plus, I'm going to take now the derivative of this, right? And the reason I can do that is because we have addition between these. So I do derivative of this one plus derivative of this. What's derivative of this? So B is attached to this, right? So B comes for the ride. What's derivative of x? 1. So B times 1 is just B. Okay, and then you take the derivative of C. And what's the derivative of C? That's a constant by itself. That goes to 0, right? So would you agree with me on this? If I write this way, that this represents the slope of the tangent line anywhere on this function. You just have to give me an x, right? Now, when you're at the vertex of a parabola, no matter which way it opens, this way or that way, when you're at the vertex, what is the slope of the tangent line there? 0. It's got to be 0, right? At the vertex? So aren't we really asking ourselves, when is this 0? When is that 0? So let's set it equal to 0. And let's solve for x. And what would happen if you solve for x? Get 2ax, subtract b from both sides, and divide both sides by 2a. And you get, this tells you what x value will give you a tangent line that's horizontal. It happens when x is negative b over 2a, and that's where the x coordinate of the vertex comes from, setting the derivative of the function equal to 0. Does that make sense? Now, in college algebra, you also study polynomial functions where you went beyond 2, didn't you? And you said, all right, well, we can graph these cubic functions. And once we got to like things with 3 on them or something like that, then you say, oh, it does that. And you would spend a lot of time trying to figure out these x-intercepts, and you would do left and right hand behavior. And we've discussed this in this class. We never talked about how we find those highest and lowest points, have we? But we can. Now we can. Because to figure out where this highest point is and where this lowest point is, we just need to ask ourselves where the derivative is 0. And we'll have it, right? So let's do one. Where's the derivative of 0? So let me give you a cubic function. X cubed minus 3x squared plus 5x plus 1. Is that not a cubic function? I could graph it, right? Let's first take the derivative. So we're practicing derivative right here. Herman. There you are. Herman, I actually knew what you looked like. I just couldn't find you. There you are. Okay. Herman, can you give me the derivative of this function? Or I was going to first ask you, can you just do derivative one by one, or do we have to worry about product rule or quotient rule?
I guess we do it one by one.
One by one, right? Term by term. This term, this term, this term, this term, because there's a bunch of pluses and minuses, so this is the best case scenario. All right, Herman, are you okay with the derivative?
Yeah.
Okay.
X cubed should be 3x.
3x, power comes down by 1.
2.
Okay, squared. All right.
Then I should do a.
Herman, what happens to this minus 3? Because it's attached to this, right?
That should be just negative 3.
Just comes for the ride, right? So negative 3 is here, and then you have to say times derivative of x squared, which is 2x. So really what's going to happen there is that 2 and that negative 3 are going to multiply to be a 6. So what we'll do later, I guess as we get more comfortable with this, is when we take derivative of this, the 2 is just going to come out front and multiply times that 3 and just become negative 6. But I'm trying to show a little bit of the work. You want to keep going, Herman?
Sure.
Okay, here,
Should be plus 5.
plus 5, and finally,
1.
plus derivative of 1, which is,
Just 1.
do you see an x? It's just a constant, right?
Oh yeah, it should be 0.
0. Okay, so that's it right there. So this is it, yes? 3x squared minus 6x plus 5. That's our derivative, yeah? Now, could we actually ask ourselves where that's 0? We could, right? And we could solve it. So if we wanted to know, if we were saying to ourselves, hey, you know, when is the derivative 0, right? If we ask ourselves that, hey, when does this happen? Then we just have to set that derivative equal to 0, and we should be able to solve it because it's a quadratic. In quadratics, we can always solve because we have the quadratic formula, right? So we set that x equals 6 plus or minus the square root of 36 minus 4 times a times c all over 2a. So I could just use the quadratic formula there? You have a question? I can help.
He's asking like how did it go from 5x plus 1 to 3 negative 3 to 2x plus 5?
This became that, this became that, this became that, and that went to 0. So the 5x becomes 5 because 5 comes for the ride, derivative of x is 1.